Now it is truly our pleasure and privilege to welcome once again Dr. J. John Rosario Jagarath, Scientist G at DRDO, and one of the most respected voices in the field of additive manufacturing, particularly for defense applications. Sir had also graced us with his presence during our previous short-term course, where his keynote address left a lasting impression on all of us. We are absolutely delighted to have him back with us today, and we thank him sincerely for once again taking out time from his immensely busy schedule to be here. Dr. John has been a driving force in integrating advanced technologies like additive manufacturing and hybrid manufacturing into national strategic applications. His depth of knowledge and passion for innovation continues to inspire engineers and researchers across the country. Today, he will be speaking on highly relevant and forward-looking topic, emerging trends, hybrid manufacturing, and multi-material additive manufacturing. We are excited to learn from his experience and insight as we explore how these emerging technologies are shaping the future of manufacturing. Sir, we are truly honored and grateful to have you with us once again. Thank you for your time and continuous support. We warmly welcome you to begin your session. Over to you, sir.
Yes, it's fine. Thank you very much for the introduction. And I am very much thankful for the organizers, and especially Professor Jinesh Jain for inviting me for this presentation. But I apologize that I could not come in person due to my actual, though the program was scheduled and I planned for this visit very long time back. But still, due to some official assignment, urgent assignment, I could not. Actually, I had to travel to some other place today afternoon, so I could not able to come in person for this presentation. But I'm very delighted to be a part of this presentation and happy with you all for this another 1 hour. And so I will go with my presentation, though it may be like a general presentation, what we have actually in DRDO and in aerospace manufacturing, what we have been concentrated and what we have been doing on additive manufacturing. I just make a glimpse of it and what are the futuristic things in that additive manufacturing which is going to transform the aerospace manufacturing. So that will be my presentation. So am I audible? Just I want to take a feedback from you all.
Yes, sir, you're audible.
Okay, so I'll go with my presentation. Just I'll share my presentation. Whether my presentation is visible?
Yes, sir, the presentation is visible.
Okay, it's in full screen mode, no?
No, sir, not in full screen mode. You may put it in the PPT mode, please.
Okay, just a minute. So,
वो शायद स्क्रीन शेयर कर रखी है सर उनको बोलो विंडो शेयर किया शायद.
No, actually I'm trying for entire screen only. Just a minute. It got closed. Just I will do it.
Okay, sir.
I'm doing entire screen. Is it coming now?
No, sir, it is still in the PowerPoint mode only.
Not in full screen mode?
No, sir.
Whether it is getting changed?
So you may stop sharing your screen once and share the entire screen. You might.
Yeah, I did the second time also. I did the same thing, but still I don't know why it is not there. Entire screen. Is it fine now? No, not yet.
Sir, it is still the same, but we may continue with this only. No issue.
Okay. So now it is in presentation mode, no?
No, sir, it is still in the.
At least this
PowerPoint
is
like
okay. At least this is okay.
Yes, sir. The vision is
Slightly
okay. We can start.
Fine, fine. Okay. So if the slides are not changing, please let me know. Otherwise, I just go again. So
Sure, sir.
so good morning to all the participants, and we are there in online and offline. So just another some 40 minutes, I'll be just discussing on the transformation in aerospace manufacturing to additive manufacturing. What are the things has been happened in the recent past? So whether my slide is got changed? So the
No,
second
sir, the slide
slide
hasn't changed.
not changed.
So we can try stop sharing once and then share the entire screen. That will work.
I did 2 times the same thing, so I'll do the repeat the same. Stop sharing. Again share. Screen and window. Entire screen.
Not Windows, sir. Entire screen.
Yes, yes. Yeah, entire screen only. Entire screen. Entire screen. Entire screen. Share. Is it coming?
No, sir, it is still the same.
Oh. At least the slide is getting changed or not?
No, sir, the slide is not getting changed.
It is showing only the first slide.
Yes, sir. So we can see your screen at this point of time.
Yeah, you can see.
Yes, sir.
At least slides now, first slide, second slide changing.
Yes, sir. It is on the second slide as of now.
Okay, fine. At least I will go again as it is. Okay. So now I am coming, I am the second slide. Okay.
Yes, slides are changing.
Yeah.
No issue.
Fine, fine. Okay. So coming to that additive manufacturing, which was used in the recent past. Actually, our Ukraine war during that time, it was used very intensively. That additive manufacturing, particularly used in the Ukraine war, actually the cold spray systems, and there was a very huge purchase of cold spray systems was used in Ukraine. And ISRO has developed a 3D printed rocket engine in last year, and it was tested, and it has claimed that the number of parts from 14 has been reduced to a single piece, and the weight has been reduced drastically to less than 1/5 or less than that. That is the claim has happened. And coming to Agnicool in Chennai-based firm, so it has developed a 3D printed engine in 2024, and Skygoat Aerospace, it is a Hyderabad-based firm, and it has successfully fired Dawan-2, an advanced fully 3D printed engine, cryogenic engine, and it was tested for 200 seconds. So that is the story. And what it comes to the DRDO, what is DRDO as explained? Actually, DRDO scramjet engine, which was completely 3D printed. So it was last year news. It was tested for 100 seconds and 120 seconds. And coming to the latest thing, which is April 25th, it was successfully tested for 1,000 seconds. So that is a story. So additive manufacturing has changed. Actually, when 2 years back we started with making an engine with which can able to withstand for only 100 and 120 seconds. Now it has been done for 1,000 seconds. So that is the thing. So why additive manufacturing attacks in different sectors? So one is, anyway, everybody knows about the part flexibility, inventory stock reduction, and reduce number of parts. And when we go for eliminate complex tooling and costly material wastage reduction can be done, and it is a green manufacturing technique. So that are the advantages we see with additive manufacturing. And the application areas where additive manufacturing is widely used in the case of defense manufacturing is that it is the optimization of shape and size and weight and number of parts, saving of resources, cost saving, time saving, and material saving, and repair replacement inventory, like you can reproduce obsolete parts and replace the existing parts, and it can be lean manufacturing. And it can be we can make complex design with additive manufacturing, like conformal cooling, lattice designs, metamaterials can be done, and we can able to do printing in space and printing in remote locations. That is advantage. If you go to the internet, you can see a lot of applications of additive manufacturing. Not very, it is very much used widely in defense sector, and it is used for making bigger hulls for ships and some boats, and making some type of 3D printed runways, which can be printed very fast and can be used for defense applications. And coming to the NASA applications, we can see that additive manufacturing is very widely used in propulsion systems, and it is transforming the way of design of propulsion systems. So that is the advantage. And when come to the DRDO, these are some of the applications that we are using for defense applications. First of all, we are using it additive manufacturing for wind tunnel models. So wind tunnel models is one of the things which is used for testing of any aero design. So to keep it in wind tunnel, so we have to go for the first test models, which is the scale down models. So the scale down models, normally if you want to make it and go for testing, it will take a time frame of approximately 4 to 6 months. So this additive manufacturing reduces that time of 4 to 6 months to only 1 month or slightly above 1 month. So that is advantage we see with additive manufacturing. And we can able to make lightweight core structures. We can replace some components with lightweight structures, and some type of structural components we can make it into lightweight by making into lattice structures, and with keeping the strength and technical requirements as same, and but weight can be reduced drastically. And we have started making some air bottles and propellant tanks, which is for high pressure systems, which can be able to make with additive manufacturing. That some case studies I can explain. And coming to some parts, sometimes actually we make the picture which shows in the bottom, the assembly prototype. So sometime before making the final part, we check it with the additive manufactured part to a plastic additively manufactured part of same shape and size. We keep it and see the assembly, whether it can be assembled and whether we can able to route the cables and everything in proper. Then take out, and whatever the corrections is needed, that based on that the final part will be made. So we save lot of time and cost. But somebody may ask why it cannot be 3D model. Sometimes the difficulty is that sometimes there will be some cable routing will be there. So those things are not able to be modeled. So that time when any compact systems are there, so this additive manufacturing in plastic parts is useful to check it, and then we can go for the final comp. So coming to any missile, so since we are working in the aerospace sector, so if we take a missile, starting from the radome, the first tip to the last control actuators and the nozzle part, we can see a lot of parts are now getting transformed to get it manufactured through additive manufacturing. Propulsion system, I can say it is already having a very good print on the additive manufacturing. A lot of components are made with additive manufacturing propulsion systems. Now control surfaces, some attempts has been made, and it is very greatly used. And radome is normally made with ceramic materials or composite materials, so it finds a lot of applications. So we'll go for some case studies. So then go for some applications. So this shows the wind tunnel model, which was made with stainless steel SS316L and 174 pH. So what advantage we are getting is, one is faster realization of this part, and here we can see there are some control surfaces are there. So in the component there are some control surfaces which are to be integrally to be machined. So those control surfaces are very thin walled, but the actual component will be bulk. So when we want to do machining and fixing those parts separately, it will be difficult. So when we do with additive manufacturing, it can be integral control surfaces, so the gap and the wood can be avoided, and even thin walls features can be able to be machined, able to be printed. So that is advantages. But only disadvantage we see in this part is that finish additive manufactured part, we cannot able to achieve better finish like N7. Normally this wind tunnel models need N7 or N6 finish, so which is less than 1.6 micrometer. So on RA, so which is not possible in additive manufactured part. So normally we have to find some type of technologies or methods to improve the surface finish. So that is the challenge, and we have worked and made the part, this one. Coming to other parts like the retainer dome, which is already made and used in some flight trials. So here the difficulty is that actually it is having a small spikes, some 3 spikes are there, which is having a wall thickness of some wall 2 mm or something like that, which cannot be able to machine with conventional process. So since it is having a 3D printing advantage, when we can able to print the part with very small thickness, we can able to make it and able to deliver the parts. So this is a air bottle, so which is having a store some air at very high pressure. So the here actually it is be done, if at all you want to make it in conventional process, to be done in 2 parts and to be assembled. But if you want to make it in additively manufactured part, it comes as a single monolithic part. So the advantage is that we can make it very faster, and we can able to get without welding can be avoided. So in this case, what we have to do is, therefore some design for additive manufacturing we have to do, because without support, getting the part in internal surface is very difficult. So we made the cross section slightly teardrop shaped cross section and modified, and then the 3D part is printed, and it has successfully done. And we did some internal surface finishing also, that is also needed for this part. So we did some chemical milling in this part, and it is successfully done. So this is the part that's shown in the first slide, that is a chamber which is used for the scramjet purpose. So it is having a lot of cooling channels on the surface, on the walls. It should be the chamber completely to be cooled when it was burning. So because at very high temperature, the material, no material can be able to withstand the heat load. So there actually we want to have the cooling channels. So cooling channels, conformal cooling channels, making this very difficult task if you want to do it with the conventional process. So it was done successfully with additive manufacture and was successfully tested. And I shown that one of the case studies that NASA is using very extensively this LP engines in liquid propulsion engines. So this is actually some type of injector, some type of nozzles. So it can be, and combustion chamber can be widely used for additive manufacturing. So because additive manufacturing able to make very thin walls and with different materials like multi-material, as was explained in that one. So we can have functionally graded materials in this part, so that wherever heat load or load is more, that region will have different material, and the other regions, then the material can be different. So these are some of the parts which shows there are some small injectors are made with additive manufacturing, and the status with having a aerofoil shape are made with additive manufacturing. It was already tested also. Coming to the technologies, I think you might have already exposed to the additive manufacturing technology, so I won't go much deeper into that one, but I'll just touch upon certain additive manufacturing technologies and how it is used in different applications. Stereolithography, I think everybody knows about stereolithography. It is the raw material will be in liquid form and it be used as a maybe like a photopolymer, which is cured with some type of UV light. As those polymers can be cured and it can be the printed. This is the first foremost that it was first type of invention in additive manufacturing. So what we can do is like we can make some type of models with this one, and we can able to make some flexible seals and washers for different applications. It was being used, and particularly some washers for tightening some electronic system, which is a flexible washers. It can be printed with this technology. Coming to F2, it is a very popular technique and it being used for different applications, and the filament is extruded through the nozzle. So it is widely used for making some type of domes and some type of what you say, actually some type of connectors or some type of brackets. That type of applications is very being used, and very wide range of materials are being done, and we can able to make some components like PEEK and PE, KE, that is other polyether ketone, and other things can be done with this material, and so it finds a lot of applications. And coming to the material extrusion technology, there is another one is the carbon fiber printing. So continuous carbon fiber is one thing which we can use with. There are different technologies are being adopted for different manufacturers, and we have one Taupeg extrusion technology which is being used for making lightweight and casings with carbon fibers. And material jetting, so it is not very widely used in defense applications, but it can be used for very commercial applications, for educational applications. It's being used. And aerosol printing, this is micro printing. So this is actually finds a lot of applications in making antennas and some sensors and embedded sensors for making in missile applications. So we started working on micro printing with additive manufacturing technologies. And binder jetting, so it is cheaper and it can be used for binders are used for making the parts, and it can be later it can be debinded and can be sintered. So the cost copper can be done with this process. So we can do ceramics can be done. So what we are printing, that as I told, that gadome part is made of ceramics. It can be done with this binder jetting technology, and lot of some ceramic plates for heat resistant shields can be done with binder jetting technology. Coming to powder bed fusion, this is a very widely used technique, and it's a lot of components are made with this technology, and it is being called with different names like DMLS, EBM, SHS, and SLM, SLS. All these things are under the same umbrella of powder bed fusion. So, but this technology is having very good precision and very accurate parts can be done, but when it comes to the size of the component which is used in aerospace manufacturing, there are some limitations. So there are some methodology we are working out to make bigger parts with this powder bed fusion. So that is the future of this technology for aerospace applications. So anyway, it's SLM and EBM. So EBM is used for certain applications when we are using some reactive materials like titanium, or we can go with some niobium alloy. So it should be done in a completely in a controlled environment in vacuum. So EBM is one of the very good technique. It can be used for such type of applications where we can go for very high temperature applications. So sheet lamination and ultrasonic additive manufacturing. So these things are very widely used for making using some thin wall sheets can be combined and it can be fused and stacked together. So one good thing is that we can embed sensors into that this type of between the stacked metal strips. So we can make a thin wall shells with embedded sensors. This is the future of this one. So direct energy deposition, this is only used for very wide applications and very large parts can be done with these parts. So, but the problem is actually the surface finish is the challenge in type of this type of components. So surface finish will get slightly worse surface finish when compared with PBF. So a lot of studies are being done to improve the surface finish on these components, but we can able to make larger sizes of this thing using this blown powder technology, the process. And wire arc additive manufacturing are wire DED. So we call both the things. When laser is used, we call it as wire DED, and when arc is used, this wire arc additive manufacturing. So which is very now getting popular and very nicely used for a lot of applications. And we have made some components with this process also for the larger size components. And hybrid manufacturing, coming to hybrid manufacturing, this again wire-based manufacturing, where instead of arc, laser is used for melting. So we can able to print as well as we can able to machine in the same machine. So subtractive as well as additive, both can be done in this technology. So we can able to make parts like blades and those things. We can save a lot of materials in this if we go with this technology. So costly materials can be saved when we go with this technology. And cold spray metal printing is one thing which I showed in the second slide, that is titanium, which is used for cold spray. So we can deposit, we can harden the surfaces of soft materials with this additive manufacturing. So we can able to deposit very high speeds of 45 kg per of material per hour can be deposited, and it can be different materials like starting from titanium, invar, aluminum, gold, everything can be deposited on mandrel, and once mandrel is removed, it can be as a additively manufactured part. So coming to another thing is that for making using the technology of friction stir welding, so similar technology is used for friction stir additive manufacturing. So the bigger size parts, so lot of bulk material addition is possible in this one. So in overall, we have seen a lot of technologies. So if you see that complete metal additive manufacturing, if you see the umbrella of metal additive manufacturing, powder bed fusion will use a lot of precision features, but the deposition rate is less. When you go with wire-based wire arc, wire DED, we can able to do a lot of deposition, but the precision will be less. So that is why in the case of metal additive manufacturing, when it comes to the composite parts, for making composites, there are different technologies. The Taupe extrusion is one of the technology which can be used for making some parts, which is already we have started working on making the parts for aerospace applications. And coming to ceramics, there are different technologies are there, starting from either vat polymerization or extrusion, or if it can be binder jetting, and different technologies. And the focus is like whether we can able to make the add-on. So that is a critical challenge. So whether it can be achieved or not, we have to see in another 3 to 4 years. So another big important thing is how to make 3D printing of propellants. So propellant printing is one of the main is a futuristic technology. So where we can able to print propellants with additive manufacturing, so that it will be faster. So propellant casting takes time, and propellant casting needs some type of manuals. So the manual to be kept, and it should be removed after casting. It creates a lot of problems and sometimes some damage to the propellant casting. So whether it can be 3D printed, some work has been already done, and whether it can be scaled to make bigger parts is another challenge. And coming to polymers, I think a lot of work has been carried out in additive manufacturing for polymers, and it can be, so the technology is well proven, and it is having a it is nicely matured, but now it can be used for improving the strength of the polymers, because the polymers for these thermoplastic materials are having very limited strength, so we cannot able to make high strength material polymers cannot. So when we want to make a high strength materials, what is the challenge? So that is the challenge for making using this polymer printing for the futuristic applications. So this shows that the wide range of things which multiple alloys are being used for making additive manufacturing. We can go for scaling up bigger scale, like bigger size components can be done with additive manufacturing. So these are things how the making that multiple materials. There one more slide is there. I show that how the multiple materials can be used in additive manufacturing. So these are in the case of propulsion, it shows a lot of applications. And so material is one of the great challenge. So how to make a additive manufactured nozzle or some component which is external will be some type of high temperature material like inconel or some material, and internal to be having some type of sorry, actually in the case of nozzle it will be inconel will be in the internal surface and external will be the cooling channels, copper will be there. So when we want to do copper as well as inconel printing together, so how it can be done. So that is one of the challenge. So whether we can make the cooling jacket as well as the nozzle, everything can be done in a monolithic piece. So that is the multi-material thing, which is a great challenge in aerospace applications. So am I audible? So whether I'm hello?
Yes, sir, you are audible.
Okay, okay. Just I'm going again. So maybe another 5 to 10 minutes I will take. So what are the challenges in additive manufacturing which you are facing? So one is starting from software for pre-processing, then feedstock materials, the equipment and processes, and the post-processing, and what are the standards evolved for safety as well as printing and quality assurance, and going for what is the skill gap and what are the intellectual property rights outputting and the digital security. These are some challenges which we are facing and different phases of this additive manufacturing. So we can see that there are actually in India there are only two equipment manufacturers which is making India, Intech DMLS and Amaze, who are making the PBF. And when you come with other equipments, you see that most of the equipments are imported. And when we want to attempt on new technologies, the manufacturers is not available, like micro printing, micro additive manufacturing. No manufacturers in the country. Ceramic printing, there's some work is being done in ceramic printing in the country, and hybrid manufacturing is some work recently is taken over. But in overall, actually, we are facing a lot of challenges in equipment manufacturing and post processing and establishing the standards for additive manufacturing and the skill gap. So our people are trained for in the taking up additive manufacturing for the future. So it is not that we have to think on the conventional process and additive manufacturing. We go with the conventional process, we replace with additive manufacturing. It's not the right methodology. So we have to design for additive manufacturing. So that concept should come. So the design for additive manufacturing should be in the skill development for our people. So they have to think how additive manufacturing, the design has to be changed for additive manufacturing so that we can use the potential of additive manufacturing in a better. So if we see the software starting from design, topology optimization, 3D meshing, process simulation, pre-printing, and process and post-processing. So how many softwares are developed in the country? It is very minimum. So if you see, only a few Indian players are there to develop the software, but otherwise if you see it is mostly imported. So somebody, some academic, some people can come forward to develop some softwares for this additive manufacturing. It can be taken up for the future. And materials, again, we can see we mostly work on these three materials like metallic materials, ceramic materials, composite materials. There are other things like smart materials, and they are printing of flexible substrate materials and printing electronic materials, high energy materials, and those things are there where the material availability is also very limited. So that is the area where for additive manufacturing. So these are the other areas where actually additive manufacturing needs inputs like starting from part design, analysis, model deformation analysis, and what are the methodologies for in situ, how to do the finishing part. And coming to the final part, how to finally validate the part. So that is the challenges. So if you see from if you take any process, it takes from starting from input material to qualification. There are multiple layers are there. So it's a lot of verticals which where actually the additive manufacturing is already in development, but there are a lot of scope for people to work on these areas to develop the technology. So in defense application, if we see, if we can go for some high entropy materials, functionally graded materials, multi-material printing is one of the challenge, and high temperature materials printing is another challenge. Then artificial intelligence, machine learning, process development. So now we are working on developing the data. Actually, we are working on getting the data. So a lot of data is getting generated for making artificial intelligence models. Even in our lab also, we are working to generate a lot of process parameters optimization as well as data generation for making artificial and machine learning models for our process improvement, and making the smart materials another challenge. And 4D printing is printing with the smart materials, and it is the fourth dimension can be either time or temperature, whatever may be. So 4D printing is one of the very new technology, and some lot of research works are being carried out in our lab. Also, we are working on 4D printing to deploy smart medicine for some applications. And lattice structures is one of the another great boon for additive manufacturing. Like we can able to use additive manufacturing for making lattice structures, and we can able to make frequently tuned structures. So when we want to have a strength as well as frequently tuning, so we can able to do with this type of lattice structures, and we can infiltrate with these things with some polymer materials, so that we can able to tune the frequency spectrum such a way what is needed for certain applications in aerospace sector. And propellant printing already I discussed, and micro printing is another thing which for making sensors, additive manufacturing, a lot of applications. And there are other applications apart from these things, whatever I discussed. There are some bioprinting, printing of implants and prosthetics, and wearable sensors and flexible electronics, and printing sensors directly on skin. Some of the areas where this additive manufacturing can be used in defense. Our soldiers who are used in the borders, so they can use energy harvesters is one of the things where we can the sensors can be printed, and they can be on the clothes. What are the clothes they are wearing? On that one, energy harvesters can be printed, and it can be used for charging the electronic devices. That is one of the things which the recent some proposals have come. So these are the wide applications of this additive manufacturing defense sector, and how it is transforming the aerospace manufacturing. These things. So coming to the concluding remarks, additive manufacturing is a technologically enabled innovation of the 21st century, and there are a lot of challenges are there. As I told, though it is additive manufacturing has come to a certain level, but there are a lot of challenges we are facing, and there are a lot of improvements and developments are needed in these things. And coming to only for making the metallic parts, if you say how to make a fully dense parts, and how to make improve the property enhancement in 3D printed parts, especially in the case of polymer parts, and how to do qualification of the parts for aerospace applications and finishing. So these are the main challenges, and a lot of R&D activities are needed in this one. So with this one, I thank you all for patient listening for this one, and I thank the organizers for giving me the opportunity to be with you in this one. Jay, thank you. So it's open for any questions, if any.
People having any doubts, please write it in the chat box.